Imagine pouring liquid nitrogen deep underground into an ancient riverbed to freeze a waterlogged swamp, hoping to save a world-famous medieval wonder, only to watch the expanding ice turn into a massive hydraulic jack that threatens to snap a 15,000-ton marble tower in two. This isn't an exaggerated engineering horror story. It actually happened in 1995 beneath the Leaning Tower of Pisa. So why was this absolute masterpiece of Romanesque architecture built on top of a hidden swamp in the first place? What is the real centuries-old story behind its notorious tilt? And when modern structural engineers finally unlocked the secret to pulling it completely straight, why did the Italian government step in and explicitly forbid them from finishing the job? To understand why the Leaning Tower of Pisa leans, you have to look back thousands of years at the geology of the Arno River, which today flows just 1 kilometer away from the site. Centuries before construction ever began in 1173, the river didn't follow its current path. Over millennia, it shifted back and forth across the plain of Pisa, depositing alternating layers of fine sand, heavy mud, dense clay, and waterlogged silt. To the ancient builders standing on top of the grass, the ground looked firm, flat, and solid. In reality, it was a hidden geological nightmare, a soft, unpredictable swamp waiting to collapse under real pressure. The city of Pisa didn't set out to create a strange, leaning curiosity. They were at the height of their military and commercial power in the Mediterranean, and they wanted a majestic bell tower, known in Italian as a campanile, to showcase their massive wealth alongside their cathedral in the Square of Miracles. In medieval Italian architecture, bell towers were traditionally constructed as separate, freestanding structures next to the main church. In August 1173, workers dug a shallow foundation ring just 3 meters deep, roughly 10 feet, and lined it with heavy stone masonry. For a 56-meter marble tower weighing nearly 15,000 tons, a shallow 3-meter foundation sitting on uncompressed, water-soaked river silt was an absolute death sentence from day one. At first, everything went smoothly. Workers completed the ground floor using solid white marble columns and intricate archways. But by 1178, as they were completing the third floor, the heavy marble weight pressed down unevenly. The soft silt beneath the southern side crushed, and the incomplete structure took its very first noticeable tilt to the south. Before the original builders could even figure out what was happening beneath their feet, geopolitical chaos broke out. The Republic of Pisa plunged into a series of long, brutal wars against its neighboring rivals, Florence, Lucca, and Genoa. Money was diverted, labor was drafted, and construction on the half-built tower ground to a complete halt. Ironically, this 100-year war saved the tower from an immediate, catastrophic collapse. During that century of standing completely abandoned, the massive weight of the lower 3 floors slowly squeezed the water out of the compressed clay beneath it. That extra time allowed the soil to settle, firm up, and consolidate. Had construction continued without interruption, the added weight of the upper floors would have easily pushed the fragile foundation past its tipping point, causing the tower to fall before the 13th century ever began. In 1272, a new generation of architects and master builders stepped in to finish the job. Looking at the 3 crooked floors, they decided against tearing down the flawed base. Instead, they attempted a classic medieval workaround. They decided to build the rest of the upper floors crooked on purpose. They carved taller, thicker stone blocks for the leaning southern side and shorter blocks for the northern side, attempting to balance out the angle as they built upward. Instead of fixing the problem, this uneven weight distribution shifted the building's center of gravity back and forth. Rather than straightening out, the tower began to curve. It turned the rigid marble structure into a giant, vertical, banana-shaped cylinder. Work halted once again in 1278 due to yet another war, with the structure sitting incomplete at 7 floors. It wasn't until 1360, nearly 200 years after the first shovels hit the dirt, that architect Tommaso di Andrea Pisano was hired to build the 8th and final floor, the belfry that would house 7 heavy bronze bells. Pisano used the exact same trick one last time. He built 4 steps on the southern side of the bell chamber and 6 steps on the northern side, forcing the bell room to sit roughly horizontal even though the tower beneath it was tilted. If you climb to the top of the tower today, those uneven stairs remain as permanent proof of medieval damage control. The tower was finally completed in 1372, but the slow-motion collapse into the soil never actually stopped. Over the next 5 centuries, gravity kept pulling the marble monster deeper into the mud. In 1838, an architect named Alessandro della Gherardesca wanted to expose the hidden marble carvings at the base of the tower that had sunk below ground level. He ordered workers to excavate a wide circular walkway around the bottom. But removing that surrounding dirt stripped away critical lateral soil pressure that had been holding the foundation in place. The ground shifted instantly, and the tower lurched another quarter of a degree further south. Then came 1934, when Italian dictator Benito Mussolini decided that a crooked, falling tower was a national embarrassment to his regime. He ordered engineers to fix it once and for all. Workers drilled 36 holes directly through the marble base and pumped 90 tons of liquid concrete straight into the subsoil. Mussolini's plan backfired terribly. The 90 tons of wet concrete didn't create a solid platform. Instead, the heavy liquid sank through the soft clay like a stone in a pond, dragging the southern foundation down even deeper and pushing the overall tilt past 5 full degrees. The ultimate crisis point arrived in 1989. In the nearby city of Pavia, another medieval masonry tower, the Civic Tower of Pavia, suddenly collapsed without any warning, crushing 4 people to death. The disaster sent shockwaves through the Italian government. Authorities rushed to perform emergency structural checks on Pisa's tower and discovered it had reached a terrifying 5.5-degree tilt. The very top of the structure was hanging over 4.5 meters out of plumb line. In 1990, for the first time in its 800-year history, the Leaning Tower of Pisa was officially shut down to the public. Emergency teams removed the massive bronze bells from the top floor to reduce structural stress. Computer modeling warned that a minor load shift of just 7%, or a minor earthquake, would cause the entire building to snap at the 3rd floor and shatter into rubble. An international task force of top structural engineers and geologists was assembled to pull off a miracle. To buy time, the team wrapped high-strength steel cables around the fragile lower floors to keep the masonry from exploding outward under the stress. Then, they stacked 600 tons of heavy lead ingots onto the northern, raised side of the foundation. That temporary counterweight pulled the tower back by a fraction of a degree, preventing immediate collapse. But lead blocks looked hideous on a world-historic site. Engineers needed a permanent, invisible solution. Their initial plan was to drive heavy steel cables deep into the earth and anchor the tower to solid bedrock located 40 meters below the surface. However, the ground beneath Pisa was saturated with water. Drilling deep holes through waterlogged clay meant groundwater would burst upward through the drill shafts, liquefying the soil and sending the tower over the edge. That's when engineers pitched what seemed like a brilliant idea: liquid nitrogen. The plan was to freeze the ground before drilling. By pumping liquid nitrogen at minus 200 degrees Celsius into the soil around the foundation, they could freeze the groundwater solid, creating an impenetrable wall of ice so workers could safely drill down to bedrock. In 1995, they tried it. It was an instant catastrophe. The moment the minus 200-degree liquid nitrogen hit the saturated subsoil, the underground water froze solid. But water expands when it turns into ice. That rapid expansion acted like a massive underground hydraulic jack right under the northern side of the building. The freezing soil heaved upward, shifting the tower's weight and forcing the entire 15,000-ton structure to violently lurch even further to the south in real time. Engineers panicked. They immediately aborted the operation, pumped the liquid nitrogen out of the ground, and frantically added another 300 tons of emergency lead counterweights to the northern side to stop the momentum before the tower fell. After surviving the liquid nitrogen disaster, the engineering team turned to a far simpler, low-tech technique called soil extraction, or under-excavation. Instead of trying to freeze the ground or build massive anchors down to bedrock, they decided to pull dirt out from under the high side. The idea was to use long, angled drills to remove tiny tubes of soil from beneath the northern foundation. As those small hollow pockets underground collapsed under the weight of the earth, the high side of the tower would sink just a fraction, pulling the entire building back toward the north. Because one tiny mistake could cause the tower to tilt sideways and collapse, the team took extreme precautions. They built a full-scale, 7-meter concrete ring model nearby to test drill angles and measure soil collapse behaviors first. Once they proved the science, they attached massive safety harness cables from the real tower to winches anchored hundreds of feet away. Workers drilled 41 slanted holes beneath the northern edge of the foundation and slowly extracted more than 70 tons of earth over several months, removing just tiny bucketfuls at a time. The technique worked like magic. As the hollow spaces collapsed beneath the north side, the high edge settled smoothly, and the tower began to pull itself back upright toward the north in precise, controlled millimeter increments. By the end of the project, the engineering team had complete control over the structure. Technically, they possessed the exact data, equipment, and capability to extract enough soil to pull the Leaning Tower of Pisa 100% straight. However, the Italian government issued a strict, non-negotiable directive: do not straighten it all the way. The tower's famous tilt was the single biggest tourism driver in the region, bringing millions of visitors and hundreds of millions of dollars to the local economy every single year. Straightening the building completely would erase its global identity, ruin its historic signature, and destroy Pisa's tourism industry overnight. The committee was ordered to pull the tower back only to its safe early 19th century tilt angle. They reduced the tilt by roughly 40 centimeters, about half a degree, bringing it to a perfectly stable 3.97 degrees. To ensure long-term stability, workers installed specialized drainage wells beneath the northern side to pump away excess groundwater, keeping the subterranean moisture level perfectly balanced on both sides forever. On December 15, 2001, after 11 long years of emergency interventions, failed experiments, and brilliant soil mechanics, the Leaning Tower of Pisa officially reopened to the world. Today, state-of-the-art sensors monitor every single millimeter of movement around the clock. Structural engineers confirm that after surviving medieval wars, disastrous modifications, Mussolini's concrete, and a liquid nitrogen freeze, the Leaning Tower of Pisa is completely rock-solid and won't budge an inch for at least another 300 years.